Consider a uniform magnetic field of strength B. Let a charged particle of charge q be projected into the magnetic field with the velocity v perpendicular to the direction of the magnetic field. When the charged particle is moving perpendicular to the magnetic field, the charged particle experiences maximum force, and this force is acting perpendicular to both the magnetic field and velocity of the charged particle. The magnitude of the force acting on the particle F is equal to BQV sin theta, where theta is the angle between the direction of the velocity and the direction of the magnetic field. Since, in this case, theta is equal to 90 degrees, sin 90 is 1, and hence the force is denoted by F is equal to BQV. We know that when an external force acting on a body is perpendicular to the motion of the body, the work done on the body is said to be zero. In other words, in the expression for work done, W is equal to Fs cos theta. If theta is equal to 90 degrees, we get W is equal to 0. In the case of a charged particle in a magnetic field, the magnetic force is acting perpendicular to the direction of velocity, and thus the work done on the charged particle is 0. As the work done on the charged particle is 0, there is no change in the kinetic energy of the charged particle, and the magnitude of the velocity of the charged particle remains constant. As the magnetic force acting on the charged particle is perpendicular to both the direction of its velocity and magnetic field, the charged particle moves in a circular path, and the magnetic force acts as centripetal force. Thus, the centripetal force F is equal to BQV. By definition, the centripetal force is denoted by mv square by r, where m is the mass of the charged particle, v is its velocity, and r is the radius of its circular path. Equating these expressions, we get the radius of the circular path, r, is equal to mv by bq. Let this be equation 1. When the momentum mv of the particle increases, the radius of its circular path also increases accordingly, as b and q are constant. Hence, the radius of the circular path of the charged particle moving in an external uniform magnetic field is directly proportionate to the momentum of the charged particle. The charged particle executes uniform motion with a fixed time period t and angular frequency omega. Here, omega is equal to v by r. Let this be equation 2. Comparing equations 1 and 2, the angular frequency of the charged particle omega is equal to bq by m. Let this be equation 3. As you know, the time taken to complete one revolution is called the time period of revolution. Time period t is equal to 2 pi by omega. Substituting equation 3, we get t is equal to 2 pi m by bq. From the expression, it is clear that the time period of revolution of the charged particle is independent of its speed. The reciprocal of time period is called frequency. That is, F is equal to 1 by T. Substituting T in the expression, we get F is equal to BQ by 2 pi m. This frequency is called cyclotron frequency. Cyclotron is a particle accelerator, which we will discuss in another module. Now, consider that the charged particle is projected at an angle theta to the uniform magnetic field, which is anything other than 90 degrees. In this case, we need to resolve the velocity into two components. One component parallel to the magnetic field, Vp, and the other component perpendicular or normal to the magnetic field, Vn. Since Vp is parallel to the direction of the magnetic field, we have Vp is equal to V cos theta. As Vn is perpendicular to the direction of the magnetic field, we have Vn is equal to V sin theta. The component of velocity, Vp, along the magnetic field remains the same because the angle between the parallel component of velocity and the direction of the magnetic field is zero, and hence there is no force acting along the magnetic field. The charged particle moves along the magnetic field due to the parallel component of velocity, Vp. At the same time, due to the normal component of velocity, Vn, the charged particle moves in the circular path, with radius r equal to m into Vn by bq. Thus, the charged particle has a velocity in the direction of the magnetic field and also in a circular path, whose plane is perpendicular to the direction of the field. Due to this, the resultant path of the charged particle is a helix. The radius of the circular path during the helical motion is called radius of the helix. Here, the axis of the helix is along the magnetic field. The distance moved by the particle along the magnetic field during one rotation in the helix is called pitch. Pitch P is equal to the product of a parallel component of velocity and the time taken to complete one revolution, which is time period of revolution. Substituting T is equal to 2 pi m by bq in the expression, we get P is equal to Vp into 2 pi m by bq, which is equal to 2 pi mv cos theta by bq. So far we have discussed the motion of a charged particle in a uniform external magnetic field. What happens if the magnetic field is non-uniform, as in the case of the Earth's magnetic field? In the case of a non-uniform magnetic field, the field lines are not straight. In this case, the helix of the moving charged particle also follows the direction of the curved magnetic field lines. During a solar flare, that is, when a sudden, rapid and intense variation in the brightness of sunlight occurs, a large number of charged particles are ejected from the sun. When these charged particles enter the Earth's atmosphere, they get trapped in the Earth's magnetic field and move in helical paths along the field lines. But near the Earth's magnetic poles, these lines of force come closer to each other. The density of magnetic lines of force increases, and the density of charges moving in the helical paths along the magnetic field lines also increases. When the density of the charge increases at the poles, these particles collide with each other and also with the molecules of atmospheric gases. Then the atoms of the atmospheric gases get excited. These excited atoms emit light during de-excitation. Excited oxygen atoms emit a green light during de-excitation. Excited nitrogen atoms emit a pink light during de-excitation. This phenomenon, when it occurs in regions of the North Pole, is called aurora borealis. It is called aurora australis when it occurs in regions of the South Pole.